In this discussion of limits, we're going to discuss calculating limits analytically. And this is the preferred method and what we use most of the time in the future. The very first technique is one that's called the substitution method, and it's just as it sounds. This is the simplest method of calculating a limit, the most obvious method, and the method that we should always try first unless we know it won't work. So let's look at several examples. First example, say we're asked to find the limit. Oh, let's go back to the original one that we started with. Find the limit of 2x plus 1 as x approaches 3. Now the substitution method says, well, we'll simply substitute the target value, because we understand what's going on here, into the expression. So we'd say 2 times 3 plus 1. Of course, that's equal to 7. And so our conclusion is that the limit would be 7. Like I said, this is simple. We should try it all the time. And of course, now you look back and say, why didn't we do this in the very beginning? Well, we saw examples where the substitution method wouldn't work previous to this. Second example, let's say the limit of the square root of x plus 1 as x approaches 5. Well, in this case, the substitution method would give us the square root of 5 plus 1, which of course is the square root of 6, which we cannot simplify any further. So our answer would be the square root of 6. Of course, here the answer is 7. Here the answer is the square root of 6. We could do something of the nature, the limit of 8 as x approaches 3. Well, in this case, there's no place to do a substitution. In fact, the result here would be a constant, and the lesson from this point of view is that the limit of a constant is always a constant, because as x gets closer and closer to 3, what happens to 8? It remains 8 all the time. It has nothing to do with the value x. So the limit of a constant is always the value of the constant. Okay. Well, we haven't had anything that's been real challenging here. Let's look at the next one. Let's suppose we have the limit of the fraction, and we've seen this fraction before, the fraction x squared minus x minus 6 divided by x minus 3. And the limit is as x approaches 0. That target point is 0. Well, in this case, when we substitute a 0 in for x, what would we get? We would have a 0 squared minus 0 minus 6 divided by 0 minus 3. And of course the numerator would simplify to negative 6, the denominator to negative 3, and of course negative 6 divided by negative 3 will be a positive 2. So there is no trouble with this using the substitution method. And once again, this is the preferred method. Now, we can't always use the substitution method, and this next example is one that we've seen previously. In fact, it's the same problem that we see above, or at least the same function, except our target point is different. So it's the limit of x squared minus x minus 6 over x minus 3 as x approaches 3 instead of as x approaches 0. And when we do our substitution method this time, we would get 3 squared minus 3 minus 6 divided by 3 minus 3. Of course, we recognize the denominator is an issue right now, since 3 minus 3 is 0. But if we calculate the value in the numerator, we'll also find we have the value 0. And when we have this situation, we call 0 over 0 an indeterminate form. And that basically tells us that we can't use the substitution method to calculate this limit. And the limit may exist, we just don't know what the value is yet. So that's what we're going to address, another technique other than substitution, and one that will serve us well on the next page. Well, we just saw on the previous page that we couldn't use the substitution method to calculate the limit that we see here, the limit of this expression, in the case that x approaches 3. We saw that it was easy if x approaches 0, and in fact it would be easy, we could do a substitution if x approached any number other than 3. But the substitution method, of course, as we just saw, substitution results in the indeterminate form 0, 0, 0. Okay, I mean 0 over 0, pardon me. And that tells us that we need to use another method. Here's what we'll notice. Let me start. We're going to actually go through the process here, and this is the way I'd like you to write it. We'll start out rewriting the limit. The limit is x approaches 3 of the fraction x squared minus x minus 6 over x minus 3. Now, when we worked with this limit previously and we were making a graph, to make the graph, we recognized that we could actually simplify this fraction. That is, the numerator. Now, we're still finding the limit of this expression, and all we're doing is taking the expression and factoring the numerator. When we factor the numerator, we get x minus 3 times x plus 2. And of course, that's divided by x minus 3. And it's at this point we recognize, and when we get this 0 over 0, many times that means we have a common factor in the numerator and denominator that we can, in fact, cancel. As we see here, x minus 3 appears in both places, so we can cancel the x minus 3. And so now, rather than taking the limit of a fraction, we have the limit of simply the expression x plus 2 as x approaches 3. And when we take a fresh look at this limit, the idea of substitution, remember that's what we want to try if we can, and the limit of x plus 2 as x approaches 3 can be done easily by substitution. So we substitute a 3 in for x, so we get 3 plus 2 or 5. And so the limit of this fraction as x approaches 3 is actually the number 5. And notice we keep the limit notation with us until we make the substitution. And at the step we make the substitution, the LIM disappears. That's when we're actually creating. So once again, this result, when we see 0 over 0 as a result, is a good idea to try to factor and simplify. Try to factor and simplify the expression we're taking the limit of. Many times you can do that. Let's look at another example where this technique comes into play. So we're asked to find, let's see here, find the limit as x approaches negative 3. This time, let's say, as x approaches negative 3 of the fraction x plus 3 divided by x squared minus 9. Now, remember to try substitution first. That's the easy thing to do. So we should always make that our first effort. And we see here, if we try the substitution method, we end up with, let's see, the limit as x approaches negative 3 of x plus 3 over x squared minus 9. If we do a simple substitution, we do a simple substitution, we would get negative 3 plus 3 for the numerator, and negative 3 squared minus 9 for the denominator. And that results in a 0 in the numerator, and you can see also a 0 in the denominator. So this is one of those uh-oh moments. That doesn't work. So we have to try something else. And what we saw a moment ago is that maybe if we can factor, maybe this gives us an idea that we can factor and simplify. So we start over. Okay, begin again. So that method didn't work. Let's see if we can take the expression that we're dealing with and factor that expression, or factor the numerator denominator. And sure enough, in the denominator, we have actually the difference of squares, don't we? So the denominator will factor as x plus 3 times x minus 3. Okay, now remember the way this goes. We don't remove the limit yet. We have not actually calculated the limit. What we're doing is simplifying the expression. And we see that this expression, we can cancel the x plus 3, so our expression simplifies to 1 over x minus 3. Now, we reevaluate. We see that whether we can try substitution again. So this time, the LIM does disappear. We replace x with negative 3. And so we have 1 over negative 3 minus 3. But negative 3 minus 3 is negative 6. And so we would write 1 over negative 6 as the negative of the fraction 1/6. So we've calculated our limit. And you can see in both of these examples on this page, we got 0 over 0 as the indeterminate form, but one actual limit was 5, and the other time it was negative 1/6. And that's the idea of why it's called indeterminate. When we see 0 over 0, we just don't know what the value of the limit is yet. Okay, this example, we're going to have to use a different technique, but let me write down what we're supposed to do. We're asked to find the limit of, as x approaches 4, of the fraction, again, x minus 4, over the square root of x minus 2. Now, as before, we try substitution first. And I know I'm being very formal about this, but if you're going to write things down, you want to be formal. So I'll rewrite the problem, the limit as x approaches 4 of x minus 4 over the square root of x minus 2. And substitution in this case would result in a 4 minus 4 in the numerator and a square root of 4 minus 2 in the denominator. And of course that's a 0 in the numerator, and since the square root of 4 is 2, we have 2 minus 2, or 0, in the denominator. And so this is that moment again that we know we have to use another method. But as we look at this expression we're finding the limit of, we can't factor either the numerator or denominator. So this requires a new technique. And that technique is called rationalizing. Rationalize either the numerator or denominator. Now, this technique is going to occur, or we're going to consider, anytime we see a numerator and or denominator that has a square root in the a binomial involving a square root, as we see here in the denominator. So in this case, we're actually going to rationalize the denominator, which is something that we saw how to do in an earlier algebra class. But before we do that, I want to remind you of some multiplication forms. I want to remind you that if we take a plus b generally and multiply it with a minus b, that the result we get is a squared minus b squared. That's something that we should have learned a long time ago. And a simple example of that would be if we took an x plus 2 and multiplied with an x minus 2, then the result we get is x squared minus 4. And that's familiar to us. But it can also apply, and we've seen this in algebra before. Suppose we have square roots involved. For instance, the square root of x plus 2 times the square root of x minus 2 also results in. Okay, well this time, in the beginning, we're squaring this first term, which is square root of x. Subtract squaring the second term, 2. And when we square the square root of x, of course, we get x. And when we square 2, we get 4. So this turns into x minus 4. And the purpose of this demonstration is to recognize that we can multiply two binomials together that have square roots in them and end up with a result that has no square root. And so that's what we mean by rationalizing a numerator or denominator. We want to convert the numerator and denominator to a new one that doesn't have a square root in it. So here's the way we'll do this problem, now that we understand that concept. When we're calculating this limit, the limit as x approaches 4 of x minus 4 over the square root of x minus 2, we're going to perform an algebraic operation on this fraction that doesn't change the value of the fraction, it only changes the form. And we can keep from changing the value of the fraction if we just multiply the fraction by 1. But I'm going to choose the value 1, which is the square root of x plus 2 divided by itself. And I think you'll agree with me, when we take square root of x plus 2 and divide by the square root of x plus 2, we really just have a big old fat 1 there. And so when we're multiplying by 1, we don't change the value of the fraction. But magically, what's going to happen here is when we multiply together those two denominators, we will end up with a denominator that does not have a square root. But recall the way we multiply fractions, we multiply together the numerators and we multiply together the denominators. So when we were starting the multiplication, it would look of this form. That's what we're actually going to take the limit of. But we saw above that the square root of x times, the square root of x minus 2 times the square root of x plus 2 ends up just being x minus 4. So the denominator ends up being something very simple. And in the numerator, we still have x minus 4 times the square root of x plus 2. And in this case, magically, we see that the x minus 4s are going to be able to cancel. So we can actually simplify the fraction to one that I think we can find the limit of by simply using substitution this time. So we're left with simply the square root of x plus 2, and we're finding that limit as x approaches 4. So upon substitution, that becomes square root of 4 plus 2, or 2 plus 2, which is equal to the number 4. So in this case, the limit is simply 4. Okay, in our next example, let me write it down, what we're going to do here. It asks us to find the limit, this time as h approaches 0. It's not an x. And our numerator is rather lengthy and complicated here, so let me write it in. The numerator has brackets, and then 2 times parentheses. In the parentheses, x plus h, and the parentheses are squared, plus a 3, close the brackets, minus parentheses, 2x squared plus 3. All of that is divided by h. So, as I mentioned, the first thing that we are normally asked to try is simply substitution. That's the easiest thing to see, to use. But we notice that here, regardless of what else we get in the numerator, we can't use substitution because the denominator, when we substitute 0 in for h, we will have a denominator of 0, which is not allowed. So I don't really know what the numerator value would be, but I know I can't use substitution. Now, this technique is, here's what I would suggest. I say we'll simply follow our nose. And that follow our nose in this case is let's simplify first, because we don't even know what this mess is in the numerator. So rather than do something fancy, let's just find out what value we have actually in the numerator. So I'm going to kind of break it into pieces. The first part of that numerator is what's in these brackets. Okay, so as we're determining what this numerator actually looks like, let's calculate that part. And to calculate that part, we need to first expand, we need to do the squaring of x plus h. So I'm going to go over here to the side and write down x plus h times x plus h. That's squaring x plus h. And I'm simply going to use FOIL to do this. X times x will be x squared. X times h will be xh, but we normally like to write them in alphabetical order, so I'll write hx. Then we have h times x here, which is another hx, and then an h times h, which will be plus h squared. So we have two terms involving hx, so it becomes x squared plus 2hx plus h squared. That's how that calculates. So when we come back over to fill that in our brackets, we replace x plus h squared with the expression x squared plus 2hx plus h squared. And then don't forget our plus 3 out here. Now, that 2 will multiply through the parentheses, leaving us, in this case, with 2x squared, 2 times x squared, and then 2 times 2h will be 4hx, and then 2 times h squared will be, of course, plus 2h squared, and then plus the 3 that we have out here. Now, that was just the first part of the numerator. So what I would like to do is I would like to determine the value of the numerator. So let me write the first part down in this fashion. Just trying to keep order of what I'm doing. And minus 2x squared plus 3. And you can see that that's actually the numerator that I have above. So that's actually the value of that numerator, or that expression. We already determined that the first part expands to 2x squared plus 4hx plus 2h squared plus 3. And we did that on the step above there, didn't we? And then because of the minus sign of, well, let's go ahead and just write that in, minus 2x squared plus 3. Now, I would encourage you or remind you that these brackets, since we don't have a multiplier in front or a minus sign in front, then those brackets really can be removed. There's nothing special going on here, so we'll remove the brackets. But to remove the parentheses in the second expression, we have to distribute that negative sign. So this says the opposite of 2x squared, and also the opposite of 3, which becomes minus 3. So both of those become minus. And now as we look at this resulting expression, notice that we can simplify. So we have a 2x squared here and a minus 2x squared there. So those will add to 0. And I also notice we have a plus 3 here and a minus 3 here. So those will also add to 0, leaving us with just 4hx plus 2h squared. Now, that's the numerator of our fraction. I think at this point what we can do is go back to calculating or finding the limit. So here's the way I'm going to approach this. I'm going to write extra, but I'd rather write extra and then not write enough. Whoops. The limit as h approaches 0, just writing the original problem down. Okay, the numerator is 2 times x plus h squared plus a 3 minus, in parentheses, 2x squared plus 3, and all of that's divided by h. Now what we found from the previous two steps is the numerator is just the expression 4hx plus 2h squared. Now don't forget the limit. All we're doing is changing or simplifying what we're finding the limit of. So we still have the LIM. But the numerator simplifies to 4hx plus 2h squared over the denominator. We still can't substitute 0 in for h. That would still give us a 0 in the denominator. In fact, it will give us a 0 plus 0 over 0, or it will give us 0 over 0 again, indeterminate form. We don't have any square roots. Maybe we can factor. So we look at the numerator, and remember, before we can do any canceling, we need to factor the numerator or denominator. And we notice, and we want to cancel out an h. And we notice since the numerator has h's in both terms, it's a common factor, so it's factorable from that numerator. So we'll rewrite the numerator as h times 4x plus 2h. All we've done is factor out an h from both terms in the numerator. And we have an h in the denominator. Now we can cancel h's, not before now. And we still haven't found the limit. We're still simplifying our expression. But now we're taking the limit of 4x plus 2h as h approaches 0. So we would try substitution at this point. There's nothing else to simplify. But this is a little different than we've done before because we are not substituting the 0 for x. It's h that's approaching 0. It has nothing to do with x. So when we do our substitution, we put a 0 in for the h value, not the x value. So in this case, the resulting limit is actually 4x. It's not a number, it's an expression. Well, this concludes part 2. What we'll see next of limits, next we're going to see part 3, which is about limits at infinity. That's when our target is infinity rather than a number.